Hi, this is your favorite Tutor Yomi Omorewa. Tutor Yomi will be looking at a very important topic this morning called isomerism. And the way I'm going to be handling the isomerism topic this morning will be from both the elementary level to a little bit advanced level. That means it is applicable to YX students, to UTME candidates, and also 100 level or 200 level students who are studying chemistry, organic chemistry in the university. Okay, so let's delve into isomerism this morning. Let's go quickly. Okay, so we're talking about isomerism. So the first question we need to ask is, what is isomerism? Okay, now the word isomerism, as you can see here, it means it's a phenomenon, right? A phenomenon is a natural occurring situation. It's a phenomenon that when a woman is pregnant, she will give birth at 9 months. Okay, so it's a phenomenon whereby two or more compounds, okay, have the same molecular formula but different structural formula. Okay, so you have that, and we're going to be looking at various examples as we go on. And so we look at how it is divided. It's divided basically into two. Two is divided into two. Okay, the recording is going. Now it's divided into two. And one, we have what we call the structural structural isomerism, and then we have stereoisomerism. So these are the two types of isomerism, okay? So the structural isomerism, it has another name. We can call it constitutional. So in case you see the word constitutional isomerism, it's still the same thing. Is that clear? So we have structural isomerism and then stereoisomerism. Of course, structural isomerism, when we say structural isomerism, what kind of isomerism is that? How do we explain structural isomerism? Let's go. Structural isomerism is a situation, okay, or a process whereby you have two compounds, and these two compounds, they have the same molecular formula, and the connectivity of the molecules, okay, are different. Okay, the order of connection of those molecules are different, right? That's what we call structural isomerism. Put it the other way around, is a situation where you have two compounds having the same molecular formula, but then the arrangement of the atoms or the molecules now is different. Okay, so that's what we call structural isomerism. And under it, we have the following. One, chain isomerism. We have chain isomerism. We have what we call position isomerism. We have what we call functional isomerism. We have what we call metamerism, and so on. I think we also have tautomerism. And then coming to stereoisomerism. What do we mean by stereoisomerism? It's very simple. It just means that you have two compounds having the same molecular formula, but the connectivity is the same. Okay, unlike this one where the connectivity, the bond connectivity, the bond connectivity here is different, but the bond connectivity here, though they have the same molecular formula as an isomer, but then the bond connectivity here is the same. The only thing is that the spatial arrangement in stereo, the spatial arrangement in the three-dimensional space is not the same. There's a kind of orientation, okay, or the rotation rather, okay, under this. And we're going to be displaying and demonstrating that. So under this, you have something that we call the optical isomerism and geometric isomerism. Actually, under this, it is also divided into what we call the enantiomer and diastereomer. Okay, so it's important you know that. So let's pick it one after the other. Let's pick the thing one after the other. So we haven't explained the two types of isomerism. What's the next thing? So we look at number one, chain isomerism. The chain isomerism is just telling you how these atoms are arranged in different chains. So you have the straight chain, you have the branch chain, and you have the one that look like the ring chain. An example of that is your N-pentane. Your N-pentane. So you find pentane in this manner. So look at it. So you have N-pentane in this manner. So this is normal pentane now. So from here now, I'm going to draw something. I'm not teaching you naming now. Naming is a different topic entirely. So we have something like this. So I might not explain in details now because I'm not teaching naming. So this is called, why this is normal pentane, this is called 2-methyl. See the methyl here, CH3 here. So 2-methyl, 1, 2, 3, 4. 2-methyl, 1, 2, that's methyl, then 4. 2-methyl butane. The parent name is butane. So by the time you check, you will find out that it has 5 carbon here. You can see it, 5 carbon. And it has 12 hydrogen. You count it, you see it. It has to be 12. Let's see it again. Let's see another thing. So we can still draw it this way. And then here, you have C. Yes. So when you look at this, this is what we'll call 2,2-dimethylpropane. Now you watch again. How many carbon do we have here? 1, 2, 3, 4, 5. But look at the first arrangement. Straight, branch, and this look like a ring, right? That's what we call chain isomerism. They are all isomers. So if you are asked in WAEC or JAM, how many isomers are there in normal pentane? There are 3. 1, 2, 3. And this is all you can have there. So this is what we call chain isomerism. So you can see the way I arrange from straight to branch, and they're using a chi member like methyl. Okay, so that's what we call chain isomerism. So that takes me to the second one called position isomerism. Position isomerism is actually very simple. It's just you changing the position of the functional group. Okay, just changing the position. Look at this, for example. Number 2, position isomerism. Okay, so you have H here, H here, H here, H here, H here, H here, H here. So here you have 1 butanol, or what we call but 1-ol. but one butanol. So now I could also change the position of the functional group, which is a OH. Okay, I could change the position of the functional group, and when I change the position of the functional group, what happened? It becomes 2 what? Butanol. It becomes 2 butanol. So what I've done in essence, 1, 2, is to move the position of the functional group OH. That's what we call position isomerism. You're just trying to shape. You could have something like 2 chloro this or 1 chloro this, just trying to move the position of the functional group, either from 1 to 2 to 3, as the case may be, depending on what you are given. That's what we call position isomerism. Okay. I just need to be sure that the recording is going, so I'm not recording in vain. So, number 3 is functional isomerism. Now, functional isomerism is a type of isomerism whereby you have 2 compounds, of course, with the same molecular formula, but having different functional group. With different functional group. A very good example is methoxymethane, which is also known as dimethyl ether and ethanol. So this is a classic example. So let's draw. So we have methoxymethane. So here you have, this is a compound. So let's draw it. Okay, so now let's take ethanol. Ethanol is this. So draw it. We have CH3. Then we have this. And then you have OH. Would you say that this structure and this structure are the same? No, they are not. Though they have the same molecular formula, but the structures are not the same. That's what we call functional isomerism. You could also try this on your own. You could try this compound. This is ethoxyethane, and then with butanol. So this is butanol, and this is ethoxyethane. So you can check it up, and you see that the structure will not be the same. So 1, 2, 3, 4. Okay, so that is functional isomerism. I'd like to show you what we call metamerism. Metamerism is a situation where you have look at it now. Metamerism is not common for O-level students. For example, you have a situation like this. Okay, so if you look at this now, for example, how many carbon do we have here? 4 carbon. How many hydrogen? 10. How many carbon do we have here? 4 carbon. How many hydrogen? No, they are all the same. They are from the same functional group called alkyl. Though they are from alkyl, both of them, but they have different structure. Why this is called ethoxyethane? This is called methoxypropane. Methoxypropane. That's what this is called. Methoxypropane. Okay, so they are not the same. Methoxy. In case you are wondering what am I pronouncing. methoxypropane. Okay, so that's it. So they are from alkyl group. Did I say they are from alkyl group? They are from alkoxy. Alkoxy. So this is the alkyl parts. So but the entire stuff is from alkoxy or from ether. From ether. Okay, so that's what you have about metamerism. Okay, so that takes me to the next thing that we'll look at, and that is stereoisomerism. Stereoisomerism. So I said about stereoisomerism, I did say that it is actually you have what we call the geometric isomerism, and then optical isomerism. Okay, so geometric isomerism is actually talking about geometry, right? From the word geometry, okay? So you have a situation like this. Let me use an example for that, because geometric isomerism is actually divided into two. Okay, so let's see something. For example, if you have so here you have chlorine, chlorine on the same line. This is what we call Sinks geometric isomerism. Why this is trans geometric isomerism. So if you see this in your WAEC or JAM in particular, and they say which of the isomerism is the following, and you see something like this, you know that this falls under what? Geometric isomerism, which is a sub or stereo what? Isomerism. Do not forget that stereoisomerism, I did say that they have the same molecular formula, you can say there, but they also have the same bond connection, you can say their bond connection. Okay, but then there's a challenge. The challenge is that the three-dimensional space or the spatial arrangement in the three-dimensional space is not the same. Okay, so you can see what's happening here now. This chlorine is here, chlorine is here, chlorine is here, chlorine is here. That's one thing about stereoisomerism, and this falls under geometric isomerism. So once you see it this way, know that that is geometric isomerism. So what is now optical isomerism? Now, for you to understand optical isomerism, you need to understand something. For you to understand optical isomerism, you need to understand these two concepts called enantiomer and diastereomer. Okay, yes, enantiomer and diastereomer. So you need to understand this concept. Imagine you have something like this now. Okay, so let's say, let's put we have okay, let me use this one as and then you have Okay. So you have something like this. Now, what is enantiomer and what is diastereomer? So you want to understand that, right? Now, when we say enantiomer, we're talking about molecules. This molecule actually, they obviously have the same molecular formula, you know that, okay? But they are non-superimposable mirror image of each other. Okay, they are, you can see what's happening here now. So this is an enantiomer. What do you observe here? If you look at the orientation here, if you look at the orientation here now, so it's like you have your palm. Can you see my palm here? So this, my right, is a mirror image of my left. You will agree with me now, right? Okay. So, but then if I now put watch, even though they are mirror image of each other, but look at something now. Look at it. This is mirror image to this, right? But if I place my hand here, they are not superimposable. They are not superimposed on each other. There is no proper overlapping. Okay, so that's enantiomer. That they are not superimposable imposable molecules, but these non-superimposable molecules are mirror image of each other. They are mirror image of each other. Please take note of that. Let me give another classic example. Imagine you have this. 1, 2, 3, 1, 2, 3, 4. Okay, maybe I should leave it this way. And then you have this, and you have this. Okay, now let me give a kind of example that secondary school students may understand very well. Let's say you have carbon this way, and this is bromine, this is hydrogen, this is methyl, and this is chlorine. Okay, chlorine. Now, this is an optical isomerism to start with, in case you see this in JAM. What makes it optical isomerism? The fact that the center, the carbon center here, we call it chiral carbon. Okay, so if that carbon at the center does not carry this four, you can see now, chlorine, methyl, hydrogen, and bromine are 4 different kind of atoms. So the center carbon is carrying 4. That means it is optically active. It is what? It is optically active. And the chiral center, the carbon, so you can see it here, is carrying 4 things. This one is attached to it, attached to it, attached to it. So all of them can touch it, they want to touch it, and they are all attached to it. So in JAM, if they ask which of the following is optical isomerism, the one that carry the 4 different stuff, okay? If these two are the same, then it's no longer optical in that sense, okay? So it has to be 4 different stuff, okay? So now you have this. And then how do you now draw the, let me put it this way. How do you now draw? So you have this. Bromine, and then so you can see now this is an enantiomer. Okay, so you can see. So for those in the university, I'm going to be showing you something. How, if I'm to find the polarity and then I'm to rotate this, I will assign this as 1. Assign it because when you look at the atomic number, this is the IS followed by chlorine, followed by carbon, the central atom, and then hydrogen is just 1. And then if I am to move now, if I am to move, I will just rotate like this. Yeah, I will rotate like that. But come here now. If I'm to move, what do you call that? When you rotate, you have something like this now. And you move like this. How does your clock move? If your clock move this way, we call it clockwise, right? If your clock move this way, we call it anti-clockwise. So watch something now, watch. So for this one, so this is my 1, this is my 2, this is my 3, and this is my 4. Hydrogen is the least, okay? Now, if you watch this, so I move this way for this. So this one now will go this way. Are you saying now that they moved in the opposite? It has to be in the opposite direction. Okay? It has to be. For those in the university, let's say for example now, if you have your original atom to be R, I know secondary school will not understand this, please. They will not understand it. It's R, and then your byproduct is XXX. I will do another video for those in the university to explain this concept very well. Now, if you have this kind of situation that you have a different chiral center giving you an entire chiral center, oh, this is what we call enantiomer. Sorry for those in secondary school, you don't understand that. But a situation where you have this, and then all of a sudden, you now have like arrow here, and then you have arrow here, whereby you could change some of them, not all of them. We call the diastereomer. A situation, if it is a pure SSA, it becomes an enantiomer. But if one of them can be altered or 2, as the case may be, it becomes diastereomer. Okay, so let's leave that. But you can see now that why this one spins this way, the other one spins. They must not spin. If they spins in the same direction as you are doing it, then you can call it an enantiomer, because an enantiomer, they must be not superimposable, mirror image. They have to be mirror image. Okay, they have to be mirror image. Okay, very, very important. And that's what makes them to even also have what we call the same physical property, like boiling point, melting point, and all those things. So they have all of those properties as similar, even though their orientation is not is altered. You can see that it's altered there. Okay, so anything different from this. Now let me show you another example that might interest you. So let's say you have what example can I give now? What example? So let me use okay, you will do it for me. Bromine here, C2 3, that's ethyl, and then let's put something in here. Let's put hydrogen here. Yes, let's put hydrogen here. So you're going to write the byproduct. I mean, you write what will be the next for me, and then you tell me which will be the X and which will be the R. Is it the one that is going clockwise or the one that is going anti-clockwise? Okay, so basically I looked at isomerism this morning, and I've talked about what isomerism is, the types of isomerism, structural and sterile. I've talked about the structure, the 4 types under it, and the 2 types under sterile. And then I've also gone a little bit ahead, showing you what we call enantiomer and diastereomer. Now, there's a video I'm going to do, and that will be for those in the university, where I need to explain in detail the difference between diastereomer, enantiomer, and mesocompound as well. Bye.